Chain rule. Chain rule of calculus. Let's pretend that you haven't been taught that you have to multiply functions out first. That means if I have to differentiate this, that's easy. All I do is multiply down and that becomes 1 less. There we are, 6x plus 10. If we differentiate that expression, we end up with that, 18x plus 30. There we are. But hang on, that and that are the same thing. So how can we end up with that expression, that derivative, and that derivative for the same thing? Of course, quite simple, because we've done that incorrectly. You cannot do that. You have to multiply the bracket out first. But what happens if that's something like to the 30, or perhaps the square root of it? How do we differentiate it then? And this brings in the chain rule of calculus. Let's first have a look at this and see. This is what's called a composite function. A composite function is when you have a function inside a function of a function. This here can be seen as y equals u squared with u equal to 3x plus 5. So we have y equals u squared and the u is 3x plus 5. Or f of x equals 3x plus 5 squared can be seen as f of x equals g of x all squared with g of x equaling 3x plus 5. So this is with the y notation, and this is with the functional notation. In other words, the outside equals the inside squared, where we look at 3x plus 5 as the inside, and the outside being something squared. Outside equals inside squared, where inside equals 3x plus 5. I'm going to do a lot of talking about outsides and insides now, because it's a looser but easier way to look at it. So let's say we have to differentiate this expression here. Then we'd have y equals x minus 2 squared, where y equals u squared and u equals x minus 2. Or, let's go to the f of x notation. Here's the f of x notation here. We would have f of x equals x minus 2 all squared, where f of x equals g of x all squared, and g of x equals x minus 2. Match the colors. And outside equals inside squared, where inside equals x minus 2. There's the outside, something squared, so the outside is something squared, and the inside is x minus 2. Here's another one. Y equals sine 2x. Oh, be careful here. The outside is the sine. Y equals sine. Y equals sine of u. And the inside is 2x, where u equals 2x. Or, in f of x notation, f of x is sine, and g of x, the inside, is equal to 2x. There we are. Outside equals sine of inside, where inside equals 2 of x. 2x. 2 of x. Gee. Right, next one. Y equals the square root of 1 minus x squared. Or f of x equals the square root of 1 minus x squared. I think that's fairly easy to see what the outside is, because it's sitting inside a housey, and there's the housey, the square root sign. So therefore, y equals the square root of, that's the outside function, the square root of, y equals the square root of, and the inside function, u, is equal to 1 minus x squared. 1 minus x squared. or f of x equals the square root of g of x, where g of x equals 1 minus x squared. You need to be able to recognize this if you're going to deal with these composite functions in calculus, and they become far more complex. Outside, square root of inside. So we look at the outside, we're blinded to the inside first, and we're going to differentiate that first. Then we say, what's the inside? Oh, 1 minus x squared. One more. Y equals 1 over 2x minus 5. Well, the fraction is the outside. Y equals 1 over that, so y equals 1 over u, where u is 2x minus 5. In functional notation, f of x is 1 over g of x, where g of x is 2x minus 5. The outside equals 1 over the inside, where the inside equals 2x minus 5. And there's your function of a function. Now, here's the rule. Chain rule of calculus says dy by dx equals dy by du. So if we look at this previous example here, what we would do is we would say dy by du, so we would differentiate this here, keeping u just as u, and then times du dx. So if I go back to here again, there. So we would say differentiate that times differentiate that. And obviously the u, once we differentiate it, we will write 2x minus 5 where the u is. Let's actually do an example. There we are. Y equals 5x plus 2, all cubed. Y equals u cubed, where u equals 5x plus 2. So we're going to find dy by du, which is 3u squared, times du by dx, which will be 5. Outside equals inside cubed, inside equals 5x plus 2. So there we are. Here's the derivative of the outside. I've multiplied down by 3, 5x plus 2. Notice, leaving the inside as is, 5x plus 2 all squared. Now we've done the naughty. We've been told exactly what we shouldn't do, and that is we've just differentiated the outside. But now we're going to make allowance for that, because now we're going to look at the du dx. And there we are, u equals 5x plus 2, u equals 5x plus 2. So we're going to differentiate that, and we're going to end up with times 5, derivative of the inside. From there we can simplify, and there is our derivative. Now if you took this bracket and cubed it out, and then differentiated, you'd end up with the same answer. And that's fine. Some may argue that it's quicker to do it that way. It might well be at this stage. But what if that's to the 10? Then you'd have to multiply it out to the 10th power. Well, there is Pascal's triangle, I suppose, but what a schlep. Here's another one. F of x equals the square root of 1 minus x squared. There's the Housey question again. Square root of, there's your outside function, 1 minus x squared, the inside function. There we are. I've written it as 1 minus x squared all to the half, because that's how we differentiate square root. So therefore, f of x equals g of x to the half, something to the half, where g of x, that something, is 1 minus x squared. The outside equals the inside to the half, and the inside equals 1 minus x squared. So now what we're going to do is we're going to differentiate the outside, f prime of g of x, leaving g of x as it is, and then we're going to multiply by g prime of x. So, here we are. Multiply down by the half, 1 minus x squared, to the minus half, because we're going to subtract 1 off there to get minus half. Notice, we leave the inside as is. We've left 1 minus x squared as 1 minus x squared. Now we are going to go here and we're going to say, yes, but now we have to multiply by the derivative of the inside. And the derivative of the inside is going to be minus 2x. There's the derivative of the inside. Right in a simpler form, I guess, there. If you wrote that as 1 minus x squared all to the half down below, that would be accepted. Usually what happens is you're expected not to write with negative exponents. But other than that, if you want to write fractional exponents as fractional and not go back to the root signs, that's fine. Let's have a look at the next one. Alright, there we are. Can you recognize the outside function? First I'm going to write that as 4 times the denominator to the minus 1, because that's how we do differentiate anyway. We have in the past, when you differentiate a single term with a monomial denominator, that's how you differentiate it. The outside is 4 times something to the minus 1, 4u to the minus 1. The inside is x squared minus 2x plus 5. Outside, 4 times inside to the minus 1, and inside x squared minus 2x plus 5. So now we're going to use this here, dy by du. So we're going to differentiate this. We're going to differentiate that, minus 4u to the minus 2. And we're going to end up with minus 4u to the minus 2. We've left the inside as is. But now we have to make allowance for the fact that we have differentiated the trinomial inside the bracket. So now we have to multiply by the derivative of the inside. There's the inside. And quite straightforward, in brackets times 2x minus 2. Now we can simplify that a little bit, I guess. There we are. And that's in simplest form, writing the negative exponent as a positive in the denominator. Once again,